We're going to have a quick module called the General Stiffness module that's going to set us up to the direct stiffness method, which almost all the computer structural analysis software these days is based upon. The essence of it really just follows along with what we've already learned about the slope deflection method, wherein we have this 5-step procedure. We're identifying kinematic degrees of freedom. We write the slope deflection equation, which is now what we're going to call a member-end force displacement relationship. We write equilibrium equations in the slope deflection equations that was certainly going to each joint and summing moments associated with that joint, free body diagram. We would then solve for the unknown member-end displacements. These were the kinematic redundancies or degrees of freedom that we identified up in the first step. Once we had those, we fed them back into the force displacement equation to get member forces. Right, again, the slope deflection method is just one specific instance of the style of technique that we call a stiffness kind of approach. Right? And along the way, that what's going to be helpful, useful models are going to be thinking about what we call springs in parallel, springs in series, which don't actually have to physically be in parallel. The thing there about parallel springs are that they have some sort of common displacement, a single displacement that we can key towards for the deformation of the member. Right? So for this coil spring problem here, assuming a rigid bar and that this force F is applied right, say in the center, doesn't have to. By static equilibrium we could figure out what those are, but that would also change some other aspects. So let's keep it simple here. If this is the case, and we assume this bar does not rotate, pulls out with in a parallel fashion, then the elongation of spring 1 and spring 2 are the same. And so that means from an equilibrium standpoint here, this force F is going to be equal to F1 and F2. And then the force deformation relationship of the spring, F equals K times delta. And because they have the same displacement, or at least some equation that we could relate to the same displacement, we can factor out the commonality, and that equivalent spring stiffness then is just the sum of those two individual ones. Common displacement is the key. Whereas what we say in series is that they experience a common force. That's typically how you identify it here. That this net elongation in this case is the sum of the elongations of both springs. From that, then, the generalized expression that we seek is F equals K delta, so F over K is the delta, and then delta 1 is F1 over K1, delta 2 is F2 over K2. Because they have a common force or some common relationship, we can then put in or substitute in, factor out, get rid of things, and we see an equivalent spring stiffness constant in that kind of form, which is the exact opposite of systems that are in electrical circuits, resistors. Right? So let's look at a numerical example here, GK1, where we're going to find the equivalent spring stiffness of the steel bar assembly, thinking about this in terms of we've got a 1.5 inch diameter, 2 inch long segment of the rod, a 3 inch long segment that is only 1 inch in diameter, and then we've got this back to a 1.5 inch one. And what we're seeking is what's the relationship between the force that we impose on here and the resulting net axial deformation that's experienced. Right? So the axial force axial deformation model is that axial elongation for any individual centrically loaded prismatic member is equal to NL over AE. Or another way to write that is EA over L times delta is equal to the axial force. Right? Now, here in this particular setting, then our equilibrium model is going to be such that our centric load P is going to be equal to the axial force in each and every one of these segments, 1, 2, and 3. Right? And that's, of course, the classic definition of a system that's in series. Right? The system force displacement model, then, that we're seeking looks something like this. 3 springs in series, in this case physically in series. There's our P. What's the delta that we have out here? And so in this case, this is going to be that our equivalent spring constant that we're looking for is going to be the reciprocal of the sums of the reciprocals of each of the individual ones. And so that will turn out to be then, because these K1 is equal to K3, they're the same one, EA over L is the K for those individual ones. That will have then L over EA for system 1 plus L over EA for system 2, and then again the K3 is the same one, so we can multiply by 2, and that would be your at least symbolic answer. We could simplify that down. We're not going to go through that here, but that's how you would begin to approach that in this generalized stiffness approach of getting the force displacement relationship for the whole thing, right? And knowing that delta tells us in what really is happening on each and every of the individual ones. We'll later call this static reduction, that we've taken 3 individual elements and reduced it down to the equivalent of just one. That one looks like